So in this unit, we're covering the fourth type of transformation. So far in the previous unit, we covered the other three, and we love them so much. All right, the first type of transformation that we went over in the previous unit was called a translation. Then after translations, we went over reflections. Very good. And then we finished that unit off with rotations. And that leads us to the fourth type of transformation, which is actually on the objectives, not that anyone ever looks. But the objective today is to be able to transform shapes using dilations. Now if we look back, hopefully you remember that translations do not change the shapes, so they maintain congruence. Reflections, sometimes they change the orientation, but not the size of the shape, so it is going to maintain congruence. And then rotations also is changing sometimes the orientation of the shape, and so it also is congruent. Dilations, however, are not congruent, but they do produce what we call similarity. Now notice the difference between the two symbols. Similarity does not have the equal part, but it has the enye thingy. Dilation is where we do change the size of the shape. So we usually make it bigger or smaller, such as this example. Let's take this rectangle. Now if I took, or square, whatever. Square is a type of rectangle. Well, if I took this square and I translated, I could just move it up and to the right, maybe. Sometimes I could perhaps even rotate it, if I could rotate it. But it's not letting me. Or sometimes you can make it bigger or smaller by, well, making it bigger in this case. So this is a dilation from where it were, radical. This is smaller, we're going to make it bigger. Or if we want, we could make it smaller. That also is dilation in it. Kind of like people say, when you turn the lights off and on, it makes your pupils go smaller and bigger. That's dilating the pupils. So it's kind of related. All circles are dilations of each other, though. We have seen these types before. In the last lesson of the previous unit, we'll look at the coordinate rules, which hopefully will look a little familiar, even though it was before spring break, so no one usually remembers. All right, properties of dilations. Ms. Williams gave her students the grid shown below with triangle ABC, which we will just outline real quick. They took triangle ABC radical in orange. They graphed on it. She then asked her students to create a triangle that was the same shape as the original triangle, but has side lengths that are 3 times larger. Micah went ahead and created a this one radical. And Nadia created these radical. So the teacher asked the class who had done this assignment correct, Nadia or Micah. Aya said they were both correct. Hendricks disagreed and said they could not both be correct because they were not in the same location in the coordinate plane. Do you agree? And why?
I disagree.
All right. Well, let's find out first. So what they did is they took the shape ABC, this triangle, and then made it 3 times as big. All right. So when they talk about 3 times as big, what they're really talking about is the lengths of the sides. So for example, AC is a length of 3, and BC is a length of 4. So AB, if we use the Pythagorean theorem on these, would be 5. So did we make all the other side lengths 3 times as big? Well, let's check from A to E. This one is 3, 6, 9er. So it's 9. Is that 3 times as big as 3?
Yeah.
Sure is. What about E to D? How long is D's? Well, let's count. 2, 4, 6, 8, 10, 12. And is 12 3 times as big as 4?
Yeah.
Yes, it is.
Whoa.
So far, it's working. Well, what's the length of A to D? we could use the Pythagorean theorem on these, right? Square root of 9 squared plus 12 squared, bam, 15. So its length is 15. Is 15 3 times as big as 5? Yes. So Nadia, we know, has done this correct. What about old Micah? How far is it from L to N? 9. M to N? 12. And once again, if we use the Pythagorean theorem right here, it would show a length of 15 for the side length LM. So it appears that Micah has also done this correctly. And some of you guys noticed that it is just taking Nadia's and moving it to the right 4 and then up 2. Or taking Micah's and moving it down 2 to the left 2. All right, so on at these. The teacher asked Micah and Nadia to explain the methods they used to create the triangles. Let's look at Nadia first. Nadia, say, using a ruler, I slid C along the line continuing to the points A and C, containing the points A and C, until my new segment was 3 times larger than AC. So that's, and then she labeled the point E. I then used my ruler to slide B along the line containing the points A and B, as shown below, and labeled the new point D. Lastly, I checked to make sure DE was 3 times larger than BC, and it was, which we have already checked. So Nadia's method seems to work, but what about Micah? What did he does? I noticed that the sloppage of the line passing through the origin and A, so let's look at these. The sloppage going from the origin to A had a rise of 1 and then a run of 2 to the right. I placed the point that corresponds to A 3 slope triangles with the rise of 1 and a run of 2 from the origin. So that means it went up 1 and then to the right 2 again, and then up 1 to the right 2 again to get L, which is the image of the pre-image. And the same method would work to go from C to N in this case. You'd go up 1 to the right 5, up 1 to the right 5, up 1 to the right 5, and that gives you N. And B as well, up 5 to the right 5, up 5 to the right 5, and then finally up 5 to the right 5. And that gives you M as well. So 3 sloppages away from the origin makes it 3 times as big. And that seems to work. Now we'll compare the two methods used. What is the same about the resulting triangles? What is different? What accounts for the differences in the triangles? So when we look at the two methods, what's the same about the resulting triangles? They're the same size. The difference is that they're in different locations. And what accounts for the differences in the triangle? It's called the center of dilation. They use different centers of dilation for these. In the previous example, Micah and Nadia both dilated triangle ABC. A dilation is a transformation that produces an image that is the same shape as the original figure, but the image is a different size. Yes, we can see that. Triangle ABC, right here, is much smaller than Micah's right here. Every dilation has a center of dilation and a scale factor, which we've talked about in 7th grade. Scale factor is something you multiply something by to get something bigger or smaller. The center of dilation is a fixed point in the plane from which all points are expanded or contracted. The scale factor describes the size change from the original figure to the image. We use the letter R to represent scale factor. I probably won't very much though. The dilation is an enlargement if the scale factor is greater than 1, and a reduction if the scale factor is between 0 and 1. What scale factor do we use to make it the same size? 1. If you multiply something by 1, you get the same thing back. In the example on the previous page, the scale factor for both Nadia and Micah was 3. However, Nadia's center of dilation was A, which was 2, 1. While Miker used the origin 0, 0.
I still haven't blinked.
We will use the examples on the previous page. We'll just use this one, right? Because the sizes of Nadia's were the same as Miker's. So AD, for example, which was 9, divided by AB. Wait, no, AD was 5, right? 15. Whereas AB was 5, and this simplifies to 3. DE, DE must have been the up and down one. So that was 12. Divided by BC, which is 4. And this simplifies also to 3. AE, which was 9, and AC, which is 3, so dividing these two gives us 3.
Wow.
Now, hopefully you remember this scale factor also was 3. We can do the same thing with old Miker. LM, which is 15, and then AB, which is 5, so when we divide these, we get 3. Then MN, which is 12, divided by BC, which is 4. This also would give us 3.
What is that? 4?
There's a 4 there at the bottom. And then we've got LN, which is 9, divided by AC, which is 3. And 9 divided by 3 is 3 as well. So all of these resulted in the same scale factor which we used, multiplying these by 3, making them 3 times as big.
Great job listening.
All right, let's complete the following sentences then. Under dilation, the ratios of the image segments to the corresponding image segments are the same. The ratio of the image segments to the corresponding pre-image segments are the same. Specifically, they came out to be the same scale factor. Complete the following sentence. Under dilation, corresponding angles are congruent. All right, complete the following sentence. Under dilation, corresponding segments are under dilation, corresponding segments are
Same.
All right, these should be parallel. Complete the following sentence. Under a dilation, corresponding vertices are always on the same line. And finally, complete the following sentence. Under dilation, segments connecting corresponding vertices intersect the center of dilation as well. All right, let's just show that real quick. The first one was, so to show that the corresponding angles are congruent, we could find the sloppage, but I'm just going to show that these corresponding angles like BAC and MLN, these correspond to each other. And then this angle ABC, which we're going to give 2 marks because it's different, corresponds with angle LMN. It is the same angle though. And then angle ACB is congruent to angle LNM. And so we mark these as well. All right, to show that the corresponding segments are parallel, AC corresponds with LN. Those are parallel. Same with CB, corresponds with NM. Those are parallel. And then finally, AB and LM are parallel. Same sloppage for both, or all 3. So to show this one, they've kind of already given you the dashed lines right here. This one in kind of a light purple goes through the origin, which Miker used as the center of dilation, through B, and then up here through M. And then it also goes from the center of dilation to A, and then also to L, which shows that those two corresponding vertices are on the same line as the center of dilation. It would work the same way for C. So if we connected this to C right here, we'd go up, well, that's not straight, but whatever, and then up here to N, which is the same line as well. Yeah, that's a little bit better. Now we'll list the points that we have up in here. A, we can see is at 2, 1. B is at 5, 5. C is at 5, 1. So that gives us those coordinates. Now we got to find the coordinates for L, M, and N. This is Micah's dilation. So L we can see is at 6, 3. Oh man.
Nice.
There we go. M is at 15, 15. And then N is at 15, 3.
Oh, so you're just timesing it.
Yeah.
3.
So when we write the coordinate rule for these, that's all we're doing is multiplying those by 3, right? All right. So we're dilating this. It's a scale factor of 3 about the origin 0, 0. And this should give us a new rule. So we just took the x and the y values, and all we did is multiplied each of them by 3. So 2 times 3 is 6, 1 times 3 is 3. Bam. And it would work for all 3 of the points. All right, we have the same coordinates for A, by the way, A, B, and C. But then we got the new rule, which gave us still 2, 1, which is A. D is at 11, 13. All right, so this one isn't quite as obvious, but if we compare it to Micah's, which we know, and this one, though, is about the point A, which is at 2, 1. So we can see it's the same thing as what we did to Micah, and his was 3 of the x's and also 3 of the y's. But then what do we do from there? Well, let's look at N and E, which correspond. We go to the left 4 and then down 2. So we're going to do that for the x's and y's. We went to the left 4 and then down 2. We should check this just to make sure. Let's do it with 5, 5. So in the rule, we're going to start with 5, 5. We're going to dilate it by this rule. And this would be 3 times 5 minus 4, which is 11. And then 3 times 5 minus 2, which is 13. And that is the coordinates for, well, B prime, which would have given us D radicale. So for dilations, when making the coordinate rule, you're always going to dilate it about the origin first, with the origin as the center of dilation, and then you'll just figure out how far you need to translate that shape, the left or the right, and then up and down. In the following problems, one figure has been dilated to obtain a new figure. Determine the scale factor and center of dilation. Determine the coordinate rule for the dilation when asked. Okay. In the picture below, triangle ABC has been dilated to obtain triangle A prime, B prime, C prime. So to find the scale factor, we just need to find the lengths of one of the original lengths, AB radicale, which is 3, compared to A prime, B prime, which is 6. So we can see that that would give us a scale factor of 2. We can use any of the other lines as well. So this is a length of 4, and then B prime, C prime is a length of 8. Which gives us a scale factor of 2. Now to find the center of dilation, all we're going to do is we're going to take a line and we're going to connect the line. We'll extend it to go from, in this case, B to B prime. So I got this green line radicale. And then I'll connect C to C prime. And wherever these two lines meet is where the center of origin, center of dilation is, which is radicale. And in this case, that is 0, 0. So from radicale, we just need a coordinate rule. So that sets us up. Since it's just about the origin, we're dilating this through the origin. We're going to keep the x and y, and we're going to multiply each of them by the scale factor 2. And that is the coordinate rule. All right, we got these two trapezoids, LMNO, and it's been dilated to obtain L prime, M prime, N prime, O prime. Yeah, that's close. So we got to find the scale factor and the center of dilation for these. So the scale factor isn't too bad. So we find the length of mn rather, which is 4, and mn, which is 2. So we can see it's getting smaller. ml is 6, and l prime m prime is 1, 2, 3, 4, 3. There we go. So we can see that the scale factor is cutting all the original values in half. Radical. It's getting smaller. Now we just got to find the center of dilation. So we'll just draw lines going from the point to its corresponding point. So n and n prime will connect as well. M and m prime right here. And you guys can see where these intersect already.
So
L and L prime. So yeah, so
-6.
they all connect right here, which is at -6,
Right.
3. And that is our center of dilation. So right here, they want the scale factor, the center of dilation, and also the coordinate rule, which is okay. And to find the scale factor, here's what we'll do is let's compare C prime B prime to CB. So CB, we're going to use a sloppage, would go down 3, and then it appears to the right 12. C prime to B prime goes down 1, and then to the right 4. So we can see each of those values being cut in thirds. 12 divided by 3 is 4, -3 divided by 3 is -1. So next up, we need to find the center of dilation. So I'm going to do the same thing we did on that last one. So I'm going to connect B to B prime, and I'll extend the line. A to A prime, and then C to C prime. And we can see, if I had drawn this a little bit better, that it does go through the origin right here. 0, 0. So the coordinate rule, we're going to take x, y, and dilate it by 1/3 around the origin, or about the origin, whatever. So we're going to take our x and y values, and we'll just multiply them each by the scale factor. So let's look at the scale factor on a these. So let's start with AB, which has a length of 4, and then A prime B prime here has a length of 8. And BC has a length of 3, while B prime C prime has a length of 6. So the scale factor is 2, it's just 2 times as big. With the center of dilation, let's find that. Alright, so I've connected all the image vertices with the pre-image vertices. And yeah, we can see that goes pretty clearly through this point, which is at 5, 5. Bam.